Okay, I should also include the other type of problem that you'll be responsible for, and that's just a straight fluid statics problems. Let's say, like the one we talked about before, where you had something that sat like here, had some welds right here, had a bolt or some sort of U thing, and some rope that held everything, and might want to know the force on those welds. Might want to know also the tension here. The geometries of those are very limited in a way. I'm generally going to stick to something that might be easy to calculate. Might be a cube that sits here in which somebody maybe welded a cylinder into, and the cylinder goes up here, and say the cylinder itself has two bolts here in which there's a cable, or maybe the cable's connected straight up, so there's a tension in both cables. Might want to know what the weld would hold here. Might want something like, instead of a like this, it might be a cone that comes down, comes up, little eye bolt with some tensioners here, some ropes filled with water, sitting in a square container. I want to know the weld here. The key is if you look back very specifically at how that problem up here was worked, that would be very beneficial for you to understand how to work these problems. In a systematic way, without numbers, here's what we do. We break, say we're looking at this one. It's a cone, say, for example, full of water. We imagine that we clip this and we look at the equivalent loads here. Let's look at the cone, for example. Here's the cone. Now, what we're doing here is we are splitting apart two things, okay? Here's the metal jacket around the water. Here's the weld. And, of course, the water sits in here, and it produces a load that looks like this. There is a force, some force of the weld. There's the tension pulling from the top, and of course this is a distributed load. But likewise, if you look at it, this same exact load here is mimicked equal and opposite here. And this load right here is mimicked equal and opposite on the fluid. So this is the fluid, this is the force, the force that the steel puts on the fluid. This is the force that the fluid puts on the steel. Now, you look over here, and you may find that there is a weight, which is equal to gamma times the volume. There's no pressure on top. You're also going to find that there is a pressure being pushed here. Well, we already included this, but now you could go down and look at the bottom section. Look at the bottom section. I'm going to just draw it in a 2D sense, so it's projected into the page here. Now, you could draw the steel body around it. Leave a little hole here for the water to, for this part where this part is welded onto here. Kind of trying to draw a decent job of it. Oops, made a mistake there. So here it is. Now what you have across the top is you have this. Now technically, what you have as well is you have, here I'll draw this in a different color. This is the force that the steel puts on the water. Okay, it grows to a certain value here. Okay, it comes across here. And then it grows to a value here. And the length of this arrow should be the same as the length of that arrow. Hopefully I did it reasonably well. Oh, and by the way, you also have the weight that sits in here. Now, this force is again attached back to this. Now, here, let's do kind of like that, kind of like this. This is the force of the weld as well. These are the same, equal and opposite there. And this pushes against the inside of this. Now, here's the contention you may have. You may say, okay, this green, all this green we have to take a look at. Now, here, let's make some adjustments here. Okay, this looks exactly like that. It's equal and opposite. All this force is doing is this, of course, is the water sitting in here trying to push or break the container. Not going to happen if you designed it correctly. So this doesn't amount to much. What does amount to much is, if you look here, I'm going to highlight it in yellow. These values, let me see, these can all be turned into one equivalent load. And for the sake of argument, I'm going to list it and say it's going to go up, and this is going to be the force that the steel, or I'll call it F tilde of the steel, pushing on the water. I've been using S and W. Now, over here, it's got to be the reverse of that. Force tilde that the steel puts on the water. Now, these should be the same value. So you start working in this arena. What you have is this pressure times this area here, plus whatever that blue weight was right there. In other words, this is the same as that. And then I got one other thing. Although these two are going in one direction, this is going in the opposite direction, so that has to be the force of the steel on the water. And you're sitting there looking at this. Then you can go through this, move this over to here, figure out some of this. This pressure times area is directly related to gamma H. I mean, it's not directly related to, it is equal to gamma H, where that's H. You have a resultant force that's helping push up this liquid here. So you have to look at things like this way. So you're responsible for a type of problem like this, where someone may ask, what's the force that the welds have to hold? Or what would be the tension? Tension in this case is going to be the total weight of the thing. But it all relates back to, in your mind, just like you did in statics, where do you want to split the thing, and then put the equivalent loads on everything. So with that, that's the other problem you're going to be responsible for, and I'll call it good there, and that's it.